Right, question 13. Electric circuits. Okay, should be fairly straightforward. This, yeah, it's a little bit of a unfamiliar situation. Certainly, the graph looks a bit unfamiliar, but it's really GCSE knowledge. This, to be honest with you. Right, so we've got a graph. What do we do with graphs? Yeah, we look at what it's a plot of. Right, it's I against V, I against V. It's an IV graph, isn't it? It's two IV graphs. It's for a filament lamp and a resistor. Why does it look different, though? Why does it look different to what we are used to? Because it's only the positives, yeah? You're used to seeing them like this, aren't you? Where it does this, okay? That's why it looks a little bit unfamiliar. Anyway, explain in terms of electron motion why the IV characteristics for the filament bulb is a curve. It doesn't get as much bread and butter physics, as I say, as this question. Really, I mean, even at GCSE, this is one of the first questions, or one of the most common questions that's asked in electric circuit questions. Why is it that filament bulbs' resistance increases when more current flows? You should really know this without even having to think about it. Higher current, more collisions between electrons and ions. More collisions means they vibrate with a bigger amplitude. Okay, if they vibrate with a bigger amplitude, then the tungsten filament heats up. If it heats up and the vibrations are more, the electrons find it more difficult to pass. So if the electrons find it more difficult to pass, the resistance goes up. Okay, try and think step by step. Okay, but that really shouldn't involve too much thinking. Determine the resistance of the resistor. It's the gradient, isn't it? Okay, it's the gradient. So how should we find the gradient? Should we go for a point here? Yeah. No. Go big. Go big. Right. Let's go with this point here. Okay, so the resistance, I reckon that's definitely halfway between 0.5 and 0.6. Okay, and it's a voltage of 8 volts. Right, resistance is voltage over current. That's the defining equation for resistance. You shouldn't have to think about that. And if you're looking in the formula booklet, we have a problem. Right, so voltage is 8. Okay, so voltage is 8, and I reckon is 0.55. Okay, so that's 14.5 ohms. Okay, 14.5 ohms. Right, the resistor and the filament bulb are connected in series. Sketch it. Just do a little sketch. Just doing something as simple as doing a little sketch like that. It helps you it might sort of turn a light bulb on immediately. You know, you might be, oh yeah, of course, there's going to be the same current through them. Yeah, just little things like that. Just a quick sketch, I think, makes all the difference. Right, now, what we got, current of 0.18 amps. So it's the same current through each. It's the same current through each. Okay? Now, what is the overall EMF? What's the overall EMF that produces the 0.18 amps? Okay? Right, so let's go to the graph. 0.18, 0.18, remember that. 0.18. Let's get rid of that. Right, from the graph, 0.18. So, like I said, just drawing those might make you immediately say same current through each. So 0.18 is here, isn't it? Okay, so when you've got a current of 0.18, the resistor, okay, going the wrong way. Wonder why it was looking unfamiliar to me. Right, a current of 0.18. 0.18 is there. Okay, now that's going to give us a voltage across the bulb of there, and it's going to give us a voltage across the resistor of there, isn't it? Okay. Now I've drawn that more accurately on my sheet, but that's looking like 0.8 volts across the filament bulb and 2.6 volts across the resistor. Yeah, all because it's the same current, because they're in series. Right, so we've got 0.8, 2.6, 0.8 to 2.6. We've got 0.8, which is which? 0.8, yes. 2.6. So the voltage, the EMF, is the sum of those two. So 0.8 plus 2.6 is 3.4 volts. Okay, that is the total supply voltage. Yeah, we can ignore internal resistance, it tells us that. Right, what have we got now? The resistor and the filament bulb are now connected in parallel. Draw it, just draw a little sketch, there you go. And we have our power supply like that. Right, what have we got now? Determine the resistance of the parallel combination when the EMF is adjusted to 4. So now the total EMF is 4 volts, but it asks us for the total resistance, or the effective resistance of the two components together. So we need the total current, don't we? We need the total current. To find the total current, we need to find the current through the bulb and then the current through the resistor and add them together. Okay? Right, how do we find the current through those? Well, if we have the two components in parallel, we're going to have the same voltage. Okay? So you can see this whole question is just the circuit laws, is just applying the circuit laws for series and parallel that you learned at GCSE. All right? But applying them to a slightly unfamiliar situation. So that's 4 volts. The voltage across the resistor is 4 volts. We can go back to our graph and do the same procedure, but in reverse, can't we? Okay, right. So 4 volts. Now we have 4 volts across the bulb, 4 volts across the resistor. So 4 is there, isn't it? Now that's going to give us a current of, that looks like 0.28, and a current of, that looks like 0.36, doesn't it? Yeah, 0.28 amps, 0.36 amps. Okay, added together, 0.64 amps. That's the total current in the circuit, 0.64 amps. So let's go back to our circuit. So we now have 0.64 amps. That's the total current in the circuit. That's the total voltage applied to the circuit. We want to know the total resistance in the circuit. So resistance is voltage over current. It's 4 over 0.64. So the total effective resistance of the bulb and the resistor in parallel is 6.25 ohms. Okay. Part A goes off on another tangent. We've got it's resistivity now, isn't it? Now, resistivity. Resistance of the filament is 14 ohms. Yeah, it's got a length, it's got a diameter. Calculate the resistivity of the metal, which I think it's got to be tungsten, hasn't it, if it's a filament bulb. Right, let's write down some, because there's a few measurements which are important here. Let's write down what we know. So the total resistance, 14 ohms. Okay, length, 0.36 meters. It's already in standard units. Right, we've got diameter is 32. Now it's micro. Micro's 10 to the minus 6. I'm just going to write down 10 to the minus 6 meters. I'm not even going to attempt to move the decimal place. I'm just going to leave it as 10 to the minus 6. That's still a number. Your calculator is more than happy to deal with it. All right? Now we want not resistance, we want radius, don't we? So what's the radius? Radius is 16 times 10 to the minus 6 meters. Again, I'm just going to leave that. Right, what do we know? What do we need to know to find the resistivity? We need the cross-sectional area. That's equal to, I believe, pi r squared. That gives us a cross-sectional area of 8.0 times 10 to the minus 10 meters squared. Okay, right, we now need to do our resistivity calculation. The equation is, right, resistance is directly proportional to length, inversely proportional to cross-sectional area. The constant of proportionality is resistivity, rho. Okay, rearranging this. Rho is RA over L, isn't it? Putting the values in, those values in, gives us a resistivity of 3.12 times 10 to the minus 8. Right, try and get to the habit. Resistivity is going to be a small number. It's always a small number. If you get a massive number, something's wrong. Unit. Okay, unit. You should know ohm meters. Okay, ohms, meters squared, meters. It's ohm meters. There you have it. Question 13.